All right, how's everybody doing? Professor Brian back, another installment of some Workout Wednesdays. Today we're going to be working on the in-class worksheet, particularly the first one. This video will be about the Chapter 7 in-class worksheet. We'll try to get through this fairly quickly, but I'm obviously touching on the main topics and the main concepts and pitfalls that we might encounter. So the first question is essentially a table discussing the molecule. I'm expecting people to be able to draw the Lewis structure in three-dimensional using wedges and dashes, be able to count electron domains, count bonding domains, give the electronic geometry, which may be different from the molecular geometry, talk about the bond angles that we expect to exist based upon that, and then whether the molecule is polar or nonpolar. Now, as far as space to work, this doesn't necessarily give us a lot of space to work on each of these molecules. So I will be using a little bit of other space to work, and we'll do that here. So if I'm not mistaken, the very first molecule was SF6. At this point, we've probably seen this molecule a few times, but it's good to continually practice these. We're looking at 6 plus 7 plus 7 plus 7 plus 7 plus 7 plus 7. And here we have 42 plus 6 is 48. We will create 6 bonds around the sulfur atom, and then we will place lone pairs around each of the fluorines. And this does in fact use all 48 of our lone pairs. The reason we can create the 6 bonds around sulfur, remember, sulfur can have an expanded octet because of its position. It's in the third period. Okay, now if we wanted to talk about counting our bonding domains and electron domains, all of the domains on this molecule are in fact bonding domains. So we have 6 bonding domains as well as 6 electron domains, okay? In this case, they're all the same. Why? Because we have no lone pairs, right? There are no lone pairs. All right, now, this is a 2D drawing, and for us to make it 3D, we need to recognize, and not necessarily recognize, we need to look at the structure and be able to determine the molecular geometry. So that's where you should be utilizing your Vesper chart, and I suggest that while utilizing your Vesper chart prior to the assessment, you get familiar with where we need to go. Well, bonds and lone pairs are columns where we can get information, and we need to go down here to 6 bonds with no lone pairs, and we see that this gives us a molecular geometry, which is what this PDF is giving us, of octahedral. Okay, now for this to be octahedral, we can also look at the diagram they've given us, and they show us the three-dimensional drawing gives us 3 molecules, in this case fluorine, sulfur, fluorine, in the z-axis, which is the plane of the paper, north to south, and there will be 2 dashed lines and 2 wedge lines. So the correct three-dimensional drawing that I will be asking everyone to be able to accomplish should have 2 wedges and 2 dashes. However, you can draw this with 5 atoms in the same plane, and there will be 1 wedge and 1 dash. Hopefully we recognize that if we were to rotate this. Now, as far as bond angles, they give us on this sheet bond angles, but you need to be able to recognize them without this sheet, and the bond angle from fluorine to fluorine would be 90 degrees, and the bond angle for the fluorines in the XY plane is also 90 degrees. So all of the bond angles here are 90 degrees, and as far as polarity goes, okay, this molecule is nonpolar because all 6 bonded atoms are the same. Now, if you don't understand why it's nonpolar, let's talk really quickly about the bonds and their dipole moment. Remember, fluorine is highly electronegative. So we actually have a bond dipole that exists in every one of these 6 bonds, pointing towards the fluorine, giving fluorine in each one of these situations a partial negative charge, creating a partial positive charge on sulfur. However, all of these cancel. All dipole moments cancel due to geometry. This may not be the case, and I apologize that I did a lot of that without switching the screen. But notice here, this is the correct Lewis structure. And in the red, I'm showing bond dipoles along with partial charges that exist because of those dipole moments. I'm showing wedges and dashes to signify that 2 fluorines are in the plane of the paper, into the plane of the paper, and then 2 are coming out of the plane of the paper, and then 3 atoms are in the plane of the paper. We have 90-degree bond angles on each of these, and as I listed, the dipole moments themselves are canceled due to the geometry of the molecule itself. Okay? So if we go back to the worksheet, we would then draw this molecule with the dashes and the wedges a little smaller, but it would look like that. And just for time purposes, I won't necessarily show the electron pairs, but we should be showing those. We have 6 electron domains, 6 bonding domains. The electron geometry is octahedral. The molecular geometry is octahedral as well. The bond angles are all 90, and it is a nonpolar molecule. If we want to talk resonance, we have no resonance here, right? We have no double bonds, etc. All right, so the next molecule is carbonate. Again, another one that we've seen consistently, but good to continue practicing. 4 plus 6 plus 6 plus 6 plus 2. 6, 12, 18, that would be 20 total. 6, 12, 18, 22 plus 2, that would be 24 total electrons. Carbon, central atom. 3 bonds uses 6. 3 lone pairs on each oxygen will be 18. That will use all of our 24. Okay. If we're talking formal charges right now, we have formal charge because carbon is not fulfilled octet. So we must fulfill octet here to give us the carbonate, the proper carbonate molecule that gives us the proper formal charge and fulfills octet on all atoms. So we have negative formal charge on both the oxygens. Now, this is the correctly drawn Lewis structure. We have, again, 3 electron domains as well as 3 bonding domains. Remember, bonding domains are just the areas where bonding is occurring, not the number of bonds. So you do not need to make a mistake here and put 4. A lot of students may do that. Okay, because of 3 bonding domains and 3 electron domains, we can go to our Vesper chart. We can look back up here and we can see that this would give us 3 bonds with 0 lone pairs, which would give us trigonal planar molecular geometry. That will also give us bond angles of 120 degrees, and based upon the nature of the 3 atoms connected to these particular this particular central carbon, we do have a dipole moment towards each of these oxygens. However, due to the angles and due to the geometry of this molecule, this is, however, nonpolar. So we have polar bonds, but still a nonpolar molecule. Now, in 3 dimensions, guess what? We don't have to change anything about our drawing, because any molecule that is drawn in trigonal planar will have all of the atoms represented in the same plane of the paper due to its nature. However, we do have resonance, and we would in fact have 3 resonance forms of carbonate, again, where the double bond exists on one of the other oxygens, right? We're not just rotating this molecule, we're actually putting the double bond on a separate oxygen. That means that this electron density from that extra pair of electrons that's bonding to carbon, that electron density can be found in any one of those locations at any given time. And from a percentage or from a statistical perspective, 33.3% of the time, right? We can think about that because there's only 3 oxygens. So this is 1 resonance form, 2nd resonance form, and the 3rd resonance form. Trigonal planar, nonpolar, because of its geometry, and 3 resonance forms, particularly because of its correctly drawn Lewis structure. So that would be how we would approach this one, and we would just draw one of those, right? And formal charges are important because it will not be drawn correctly without a trigonal planar for both, right? And the reason these are the same for both is because we have no lone pairs. Bond angle 120, also nonpolar. Okay, now let's talk what I have to be NF3. So if we talk NF3, also familiar, we've looked at this one in class. 5 plus 7 plus 7 plus 7 is equal to 7, 14, 21, 26. We have nitrogen as a central atom because of its lower, or what is perceived to be a lower electronegativity. In this case, it may not be. And we're going to take a look at the electronegativities of each of these because it's not necessarily intuitive. But the correct Lewis structure involves creation of 3 bonds using 6 electrons, 3 lone pairs on each fluorine, well, in this case, fluorine is highly electronegative, so we do expect it to be of higher electronegativity. And then the lone pair on nitrogen. This does, in fact, use up the 26 electrons, 8, 16, 24 in the lone pair. Now, we do not have any resonance, so we have no resonance and no lone pairs. Okay. When we think about the molecular geometry, we need to go to our Vesper chart, and we see that four electron domains is here, but 3 of those are bonds and 1 of those are lone pairs. So we are dealing with trigonal pyramidal. And we also see that trigonal pyramidal gives us a bond angle of less than 109.5. And that is occurring because the lone pair that exists and sits in this position is actually pushing these bonds down, right? This lone pair are pushing those bonds to give us less than 109.5. The true tetrahedron is exactly 109.5. So we are dealing with that now. Let's talk a little bit about bond dipoles. We expect them to be towards fluorine because of the electronegativity values. And if you were in a situation where you would need those, I would give those to you. So let's take a look here. Fluorine at an electronegativity of 4. Okay, so we got 4.0 minus 3.0 equals 1.0. So the electronegativity difference is equal to 1.0. So we expect the bond to be polar. Right here, I'm showing you that these bonds are polar, and we expect that. Okay, therefore, we are going to expect partial negative and then our partial positive to exist on the nitrogen. So when we talk net dipole, it's best for us to look at this from a 3-dimensional standpoint. So the best way to draw this 3-dimensionally is to essentially expect the lone pair to be in the plane of the paper, expect one of the fluorines to be in the plane of the paper, the nitrogen also on the plane of the paper, but having one fluorine coming out of the paper using a wedge and one into the paper using the dashes. We are still assuming the less than 109.5 bond angle, but now when we take a look at these bond dipoles from a physical standpoint, from a 3-dimensional standpoint, our net dipole should be down and coming from the center of the nitrogen atom. So we do have a net dipole. This then tells us that we have polar molecule. This is very important to be able to, one, draw these and be able to determine whether the molecule is polar or not. So nitrogen trifluoride, we do expect to be polar due to its molecular geometry, bond dipoles, and net dipole. However, no resonance forms. So you have to be able to draw that as well. And we'll go back here and draw NF3. 4 electron domains, 3 bonding domains. The electron geometry is tetrahedral. However, the molecular geometry is trig pyramidal. Bond angles less than 109.5, and it is in fact polar. So we have 2 more, and we'll do a part 2 of this video for the rest of the worksheet. We are looking at hydronium ions. So when we get into acid-base chemistry, which will be coming up when we start talking about chemical reactions, but hydronium is the ion in water that makes water acidic when we talk about acidity. So from a valence electron standpoint, we're dealing with 3 or let me be consistent, 1 plus 1 plus 1 plus 6 minus 1 because of this positive, right? This is one of the few that we've seen that's positive. We're subtracting an electron here. So we are now dealing with a total of 8 valence electrons. Oxygen is, in fact, the central atom. It has to be because hydrogen cannot form really more than one bond, right? We don't see that happen because it only has a 1s orbital, right? So we create these 3 bonds, and then we use a lone pair that will in fact use up our 8 electrons. So here is the hydronium ion. When we talk formal charge, oxygen will have the formal charge. How do we get that? Remember our equation: ground state minus Lewis structure, and that would be 6 minus 5 for oxygen, which gives us 1, and that's where we get a +1 charge from. There's also no resonance here. We don't have double bonds. Okay, when we want to talk bond dipole, we can take a quick look at our electronegativity chart, and we see oxygen and hydrogen have a large difference, right? Large difference here. We have 3.5 minus 2.1. So this is equal to 1.4. So our change in electronegativity is equal to 1.4. So we're looking at what is essentially a highly polar bond, but it is towards the central atom, in this case, oxygen. And that's going to create a partial positive on hydrogens and a partial negative on our friend oxygen. So we do expect this to have polar bonds. We need to know a little bit more about our geometry to determine whether it's going to be a polar molecule. So if we take a look at our Vesper chart, we see we're in another scenario with 4 electron domains. However, only 3 bonding domains. Based upon our chart, we see that this is trigonal pyramidal with less than 109.5 due to the lone pair. And generally speaking, they tell us it's polar as a function of its geometry. So bond angle less than 109.5. We already see that these bond dipole moments are towards oxygen, but to draw this properly, again, leaving the lone pair and 1 bond in the plane of the paper, we then need 1 wedge and 1 dash, which shows us the trigonal pyramidal geometry in 3 dimensions. And now we should recognize, again, and I apologize, I wrote these in the incorrect direction. These should be towards oxygen, which will give us a net dipole in the z-axis where oxygen resides and the lone pair resides. And so we would have a polar molecule. So hydronium ion is in fact polar. And let's not forget our formal charge here of plus. So we do have a polar molecule here, no resonance, high electronegativity difference, which creates for us that situation of polarity. Electron domains 4, bonding domains 3, electron geometry tetrahedral, molecular geometry trigonal pyramidal, and again bond angles less than 109.5, and of course a polar molecule. Last, we'll work with carbon disulfide, and let's take a look at CS2. So valence electrons, 4 plus 6 plus 6. Carbon as a central atom, creating 2 bonds, each to sulfur. And we have used up 16 of our valence electrons. Now, we do not have octet fulfilled, so we would need to create a double bond. We still do not have octet fulfilled, so we would need to create another double bond, and we find ourselves with the actual and final Lewis structure for carbon disulfide, right? And if we think about this from a standpoint of formal charge, you can see that the formal charge is still 0 on all of these, right? But we do not have octet fulfilled. So this is, in fact, our final structure. Now, if we look at it from a geometric standpoint, we see with only 2 bonding domains, we're always dealing with a linear situation. As we see at the top, 2 bonding domains or 2 electron domains, we're dealing with linear. We have 180 degrees bond angle. Now, we do see that this says nonpolar, but this is not always the case, as they put a little number here, which is like an asterisk. That all depends on what molecules are around the central atom. And again, 180 degrees here. Let's take a look at the electronegativity difference though. Carbon and sulfur are effectively the same. So let's take a look. The change in electronegativity is 2.5 minus 2.5, which is equal to 0. So we actually are in a situation where we have no bond dipole. We essentially have about as evenly sharing of these electrons as you could have, okay? So we would automatically know that this is nonpolar just based off of these values. This is nonpolar. It really wouldn't even have anything to do with the electron geometry, but it's nonpolar just off of the strength of the nature of the 2 atoms. So we are dealing with a linear molecule. It is nonpolar, and we do not need any wedges or dashes because these are in the same plane. In this case, they could be in the X, let's say, in the X Z plane. Now, as it pertains to resonance, there is no resonance, even though there are double bonds, because both bonds are double bonds, so there is no resonance or moving of those double bonds to create a equivalent structure. So carbon disulfide would have 2 double bonds, 2 bonding domains, 2 electron domains, and the electron geometry and molecular geometry both linear. Bond angle 180. It is nonpolar due to the electronegativity differences. So we have walked through every one of these. We did not necessarily speak on hybridization, and we'll talk about that in some later workouts, but this is me walking through drawing a Lewis structure, showing resonance, showing molecular geometry, showing bond angle. You need to be able to do all of this. Again, please utilize your Vesper chart and utilize your electronegativity table. Just a basic one works, and you will be provided those values if necessary. Again, if you have any further questions, let me know.